Continuing on with the formalism of quantum mechanics, we're going to talk about Hermitian operators and eigenfunctions. We'll start by defining a Hermitian operator, talk about determinate states, then we'll talk about discrete spectra, and then we'll talk a little bit about continuous spectra. So, the expectation value in an observable Q of x and p can be written as the angle brackets around Q, expectation value of Q, and then you have Q sandwiched between two wave functions, psi star and psi, integrated dx. And this can be written in the Dirac notation that we already mentioned before as psi Q psi. So bra psi and ket Q psi. So Q operates on psi. Since any observable quantity must be real by definition, because otherwise you couldn't observe it, then Q must be equal to Q. The expectation value of Q must be equal to the expectation value of Q star, complex conjugate. And so we can write down that the bra psi ket Q psi must be equal to bra psi ket Q psi complex conjugate. Well, remember, we just talked about the fact that if you take an inner product of two functions and take its complex conjugate, then that's going to be equal to because this is real, if it's real, it's going to be equal to the inner product of the functions reversed. So fg star is equal to the expectation value of the inner product of gf. And this is nothing but an inner product. So because of that, when you take the complex conjugate of this bracket, it must be equal to q psi psi. And so that means that you can take this operator, Q, which is an operator of an observable, right? If its expectation value is an observable, you can take it from the right side to the left side of the bracket and put it on the other side without any problems. This is the definition of all operators which represent observables. And you can write it in general like this. So F bracket QG is equal to QF bracket G. And this operator is said to be Hermitian. That's the name of that kind of operator. So a Hermitian operator is one which you can move from one side of the bracket to the other side of the bracket without it changing form. Effectively, it's an operator that is its own Hermitian conjugate. So let's take a look at some operators that we know about. Is P Hermitian? So we can tell that by writing down F and then PG bracket, which we can write as an integral from minus infinity to infinity of F star H bar over I dg dx integrated by dx. Right? That's just this inner product. If we now take that inner product and apply an integration by parts, so that this is dv and this is u, this is dv and this is u, we get h bar over I uv, which is f star g, evaluated from minus infinity to infinity. But of course, this is going to go to 0 because the functions are well behaved and they go to 0 to infinity. They're normalizable. And then you have minus the integral from minus infinity to infinity of h bar I. And now we've moved, take the du and integrate, and from dv you go to v. And du is just df star dx, and v is just g, and you still have the constant h bar over I carrying over. This goes to 0, as I said before. And so this is equal then to, if you look carefully here, this integral, I can bring this in, make this a minus I, and then this is also a complex conjugate. So I can regroup this together as h bar over I, df dx, all complex conjugate, times g dx integrated from minus infinity to infinity. But this is just the operator p applied to a complex conjugate. It's what exists in the bracket. And this is just can be written as pf bracket g. Because of this, p is clearly Hermitian, because I started over here on the right side, applying it to g, and I can manipulate it with a simple integration by parts and bring it over to the left side and apply it to f. And these are equivalences. So, suppose we have many systems all prepared in the same way, and we measure the expectation value of Q, which is an observable, on each system. If there's a determinate state for the system, we will always get the same answer, little q. That is, in that case, the standard deviation of q must be exactly 0. This is exactly the problem we have with the infinite square well. If you prepare all the systems in the ground state of the infinite square well, and you measure the expectation value of q on all these systems, you will get the ground state energy of the, or whatever property, energy, momentum, whatever, you will get the ground state value for that. Well, what that means is that 0 is equal to sigma squared of q, but sigma squared of q is simply q minus the expectation value of q quantity squared, all expectation value of that. And we can replace the expectation value of q as little q because it's always little q, right? And so this inner product, this expectation value, is merely an inner product of psi with q operator minus q expectation value quantity squared applied to psi. Since q is Hermitian, then q minus little q, which is just a constant, must also be Hermitian. And so I can rewrite this as bringing the q minus q, one of those two, I bring it over to the left side, right? Because this is two of them. And when I bring one of them over, I take it, I peel it from the left side here, and I apply it to the left side over here. And so I'm left with one on the right and one on the left. So it's q minus q applied to psi, inner product with q minus q, little q, applied to psi. The only function whose square integral vanishes is 0, right? Because that was the definition that we had. So the only way it can be 0 is if the function is 0, itself is 0. The only way the square integral is 0. And so consequently, q operator minus q applied to psi is equal to 0. Well, what does this define? That means that q operator applied to psi is equal to little q times psi. This is called an eigenvalue equation. It's an eigenvalue equation for a determinate state. So the operator q applied to a wave function psi gives you an eigenvalue q, the only value you get out of that, times psi. And so psi then is said to be an eigenfunction of q with eigenvalue little q. We'll be using these terms a lot. So determinate states, ones where you always get the same expectation value, are therefore eigenfunctions of the operator q. So the determinate states of q are eigenfunctions of Q. So let's take a look at some properties of eigenfunctions. An eigenfunction multiplied by a constant gives the same eigenvalue. That is, if I take Q and apply it to A times psi, this is just a constant, I can pull it out. When I apply Q to psi, I get little q, lowercase q, and that's just a constant, so I can pull it out. And so I get Q operator applied to A psi is equal to Q times A psi. 0 cannot be an eigenfunction. That's another thing that we have to say. And the collection of all eigenvalues of an operator is called its spectrum. If two linearly independent eigenfunctions have the same eigenvalue, they're said to be degenerate. And remember that you can prove that for one-dimensional functions, you cannot have degenerate states. But this is not the case in 3 dimensions. So you can have degenerate functions in 3-dimensional space. The determinate states of the total energy, therefore, are eigenfunctions of the Hamiltonian, right? Because the expectation value of the Hamiltonian gives you the energy. So for a time-independent Schrödinger equation, the Hamiltonian applied to psi is equal to E psi. Finally, if the spectrum of an operator, remember that's all the eigenfunctions and all the eigenvalues of the operator, are discrete, if that spectrum is discrete, that is, the eigenvalues are quantized, then the eigenfunctions lie in Hilbert space and are physical states. Okay? Discrete does not mean that it's not infinite. It just means that it's quantized with the value n. And therefore, these eigenfunctions lie in a Hilbert space and are physical states. That's no without proof. If the spectrum is continuous, though, then the eigenfunctions are not normalizable and cannot represent physical states. So an example of a continuous spectrum is the free particle solutions. The free particle can have any value of the momentum of the wave number k, and that is continuous. It's not discrete. It doesn't have a quantum number. It can be any value whatsoever. And we know we can't normalize those wave functions. And those wave functions don't represent physical states. You need to make them into wave packets to represent physical states. So let's talk first about discrete spectra. Discrete eigenfunctions of Hermitian operators have 3 important properties. The first one is that the eigenvalues are always real. So QF applied to F is equal to little q times F. And if I take the inner product of F and QF, it must be equal to the inner product of QF and F because this operator is Hermitian. And if this gives me a value q times F, then I have the inner product of F and F times Q is equal to, on this side, I must be getting the complex conjugate of Q because the complex conjugate is inside the bracket on the left side, times the inner product of F with F. And therefore, because these are equal, then Q star, the complex conjugate of Q, is equal to Q, or Q is real. So all observables are real. Makes sense. The next thing is that eigenfunctions with distinct eigenvalues are orthogonal. We can write that as follows. Q applied to G, let's say, gives me an eigenvalue Q prime times G. whereas q applied to f gives me little q times f. So these are two different functions. If I now take the inner product of f with qg, because q is Hermitian, that must be equal to the inner product of qf with g. And so this term gives me q prime. This term gives me q. Right? Q applied to f gives me q. Since q is observable, this is real. You can just pull it out and make it a q. And over here, q applied to g gives me q prime. Now notice that the inner products here are the same inner product. So we can cancel them, and this leaves us with the fact that q prime is equal to q. And so the only way for these not to be equal, if these are distinct eigenvalues, is that the inner product has to be 0. That means that q and g, f and g are orthogonal to each other. One note, we said you can have degenerate eigenfunctions and degenerate eigenvalues. It's still possible to choose orthogonal eigenfunctions by taking linear combinations. And finally, 3, the eigenfunctions of an observable operator are complete. That is, the eigenfunctions span the Hilbert space and allow you to make any arbitrary function out of them. We're not going to prove this, but it's an axiom that comes from Dirac's equations. What about continuous spectra? Well, for continuous spectra, things are a little bit more complicated. Eigenfunctions of continuous spectra, like plane waves, as we mentioned before, cannot be normalized. Therefore, because they can't be normalized, the proofs that we just did for discrete functions of reality of eigenfunctions and orthogonality will fail, since they depend on being able to compute the inner products. And you can't compute an inner product that's bounded. However, we can beat this if we relax our standards a bit. There's a way that you can get a sort of normalization and a sort of orthogonality for continuous spectra as well. And we'll show that later on.